Okay, so welcome to today's colloquium, and thank you for coming, even though it's at an unusual day and time. So it's a great pleasure to introduce our colloquium speaker today, Ignacio Cirac. Ignacio obtained his PhD in 1991 in theoretical quantum optics from the University of Madrid. Following his PhD, he took up a professor position in Spain from 1991 to 96. From 1996 to 2001, he was a professor at the University of Innsbruck. And since 2001, he has been the director of the Max-Planck Institute in Quantum Optics in Garching. So Ignacio is a leader in the field of quantum computation and quantum information as applied to many particle systems. And he's played a leading role in bringing many of these concepts to the condensed matter community. I mean, this is how people like me are aware of his work. His work has also been recognized through many awards, such as the Max-Planck Award in 2018, Hamburg Prize in 2015, and the Wolf Prize in 2013. And so with this, I'll let Ignacio give his talk. However, I want to make some housekeeping points. One of them is that Ignacio says that he's happy to entertain questions during the talk. So if you have a question, just unmute yourself and ask it, or write it in the chat box, or just raise your Zoom hand. So with that, I'll let Ignacio start.
Okay, thank you very much, Aditi. So it's my pleasure to be here. And so first of all, I would like to thank the organizers of the colloquium for this very kind invitation, and Aditi in particular for the correspondence and also the patience that she had changing my timetable and everything else, because I was supposed to come in March to give this colloquium. But 2 weeks before we had the trip prepared, and I mean, the situation went very, very badly here in Germany, and we decided to cancel. So I'm very happy that now can happen again. So the title that I'm giving is a little bit different from the one that I was planning to give in March. So in both cases, I wanted to talk about solving quantum many-body problems. And so it's attacking these kind of problems from the point of view of quantum information, but whereas at that time I was planning to use some techniques to show how with some techniques you can solve some of these problems, some techniques, based on tensor networks. It's a specific way of describing many-body systems, inspired somehow with some of the concepts that were developed in the context of quantum information theory. Here, I decided to change and to attack the same problems to show how you can attack some of the problems in quantum many-body systems, but now using quantum computers. So the other talk was about classical computers, and now this is about quantum computers. So in fact, as Aditi said, I'm coming from the field of quantum information, and some time ago we stumbled on the fact that, I mean, that actually the problems that we deal with in quantum information and quantum many-body systems have many things in common. So if you want in quantum many-body systems, condensed matter physics, or in the fields, you have many particles, and then it's very difficult to define the physical properties of these many particles. In quantum computing, you have many qubits that you would like that they do something that you cannot describe with classical means. And so I think that there has been during the last years a lot of talk between the two communities. We have learned a lot. In my case, I have learned a lot from the condensed matter physics community. And so this talk is a little bit about that. So again, so connecting these two fields, which are already very well connected. And so I want to say that the specific results that I will show here were developed by the people that you see here on the left. It's Marie-Carmen Banyuls, Jiming Ge, Siri Lu, and Jordi Tura. So Marie-Carmen Banyuls is a staff member in our institute. Jiming Ge just finished his PhD, and Siri Lu is starting his master here in our institute, and Jordi Tura is did a postdoc with us, and in November is moving for a position in Leiden. Okay, so you probably saw this picture many times. So that's the picture of the Google CEO, and so it says next to dilution, the refrigerator, where Google demonstrated quantum supremacy. So they built a superconducting quantum computing that had many errors, but it was powerful enough to solve a problem that you cannot solve with classical supercomputers, or that it would take much longer to solve with classical supercomputers. And in fact, this is not the only case where you can see that quantum devices are catching up, and in some cases can even overcome the power of supercomputers. But there are now many say platforms in which this is happening. So we have platforms based on photons, platforms based on neutral atoms, which are trapped in optical tweezers, and then one can store information in each of them and make them interact at will, or trap ions, in which you can also trap them in the vacuum and then make them interact, and according to how a quantum computer should work, or molecules or embedded atoms in diamond or in silicon, or quantum dots or superconducting. So there is a large variety of systems, and you can expect that in the next, let's say, 5 to 10 years, many of these systems will allow us to have something like 100 to 1,000 qubits well under control. And this is even a bit noisy. So, and this is what is called in the jargon NISQ devices, noise intermediate scale quantum computers, or even some of these devices are already now available as an analog quantum computer. So maybe you cannot run universal software, it's a quantum software of them, but some specific software, so they are dedicated computers. And so the question is, what can you do with this computer? So with a Google computer or these new platforms, so is there anything that you can do that you cannot do with supercomputers? And so that's a very active area of research. So people are looking at very different problems, but most of the problems that have been developed for quantum computers, they don't work if you have errors, and that's why you automatically eliminate many of the problems that we know where quantum computers are useful. So there are not that many that could be run in this kind of, let's say, prototypes. However, I want to mention that we know that actually there is a kind of problems that we know in which you could have a big advantage even if you use one of these devices, and it's solving many body problems. And actually this is another active area of research. So how to use these devices, these analog computers or these NISQ devices, in order to solve problems that are difficult to solve with classical computers. And these many body problems actually appear in many areas of science, or in chemistry, because you have electrons that are interacting with each other, and in complex molecules, these problems get very difficult, or in condensed matter physics, where you have electrons also, or spins of atoms that are having the complex dynamics, or in high energy physics, where actually you have many particles or gauge fields or whatever that are also give rise to very complex dynamics. And people talk even about black holes. If you want to study some properties like scrambling of information in black holes, that's difficult with classical computers. So in all these problems, at the end, things boil down to having some lattice. So you can either discretize the space in the case of chemistry, or maybe in a solid, it's already discretized because of the position of the ions, it's already discrete. And then you study some systems in this discretized space, in this lattice. This could be, for example, electrons, or I mentioned nuclear spins, or it can be some gauge bosons or whatever, depending on the theory. And so you can describe the interactions among themselves in terms of some Hamiltonian. And you have to describe the physical properties of the system, and this system behaves according to the rules of quantum mechanics, even if these systems are the simplest that we can imagine, like spin 1/2 particles or qubits. Then you write the state of the system. So you want to describe the physical property, you will have to write what is the quantum state of the system. And if you write it, it will be a linear superposition of all possible configurations, of the configuration in which all spins are down, or all the spins are down and one is up, and so on. And if you have n of these particles, then in the case of spin 1/2 particles, it will be 2 to the n configurations, and therefore you will have 2 to the n coefficients in order to describe your system. If you have larger spins or electrons that have 4 degrees of freedom, then it will even be more coefficients. So in practice, this means that you want to solve these problems with a classical computer, then the memory, in order, you will have to store these coefficients, so the memory will have to grow like the number of coefficients, so will have to grow exponentially with the number of particles that you have, or lattice sites. And also, if you want to do any computation, you will have to compute at least, for each coefficient, you will have to do at least one computation, so the number of computations will be also proportional to the number of coefficients, and since they are exponentially many with the number of sites or the number of qubits, then the time will also grow exponentially with n. And that's something that, because we all know that in quantum many-body systems, then you want to describe them, then the problem goes out of memory and out of possibilities of supercomputers very fast because of this doubly exponential behavior, both in memory and in time. In fact, so people have figured out whether what happens, you could trade maybe memory by time. So maybe you can say, what happens if our memory is not exponential? So you have only a memory to accommodate some number of bits. So, and you want to solve a many-body problem, then it turns out that then it's even worse, because then the time, of course, the memory is now linear in n, but the time can be even exponential of an exponential, so 2 to the n to the power n. So this shows that even if we have, I mean, if we want to save resources in memory, then we'll have to pay much more in time, and the problem will not be exponential, it will be super exponential. And that's something that was recognized many years ago by Feynman and other people, and they say that, okay, that probably we are trying to solve these problems in the wrong way, because we're trying to solve a quantum many-body problem with a classical computer. And so he said that if you want to solve a quantum many-body problem, you'd better work with a quantum system. So what he proposed in this very famous paper is to, well, he was talking about quantum field theory. So he said, well, let's first discretize space, and let's one of these qubit, one of these spin, one half particles in each of the vertex of space. And then the state that you want to describe actually will be the state of the qubit. So in order to store the state, you will prepare the qubits in this particular state. So in order to describe n qubits, you will need n qubits. So it's not an exponential resources what you need, but just linear resources. So in fact, this is the idea of quantum simulation and even the idea of quantum computers. And what you get right away, just by storing the state of qubits in qubits, not in classical bits, you get that the memory only grows linearly with the number of qubits that you want to store, because you will need as many qubits as the one that you want to store. However, what is not clear is how the time will grow. So maybe the time grows linearly or grows exponentially or double exponentially. And actually, if we want to see if there is an advantage of a quantum computer with respect to a classical computer to solve many-body systems, then we should compare this time with this 2 to the n to the power n, because in this case of qubits, then we have only polynomial number of a polynomial growing memory in n. So if we have a classical computer with polynomial memory in n, I mentioned before, then you will have a computational time that will scale like 2 to the n to the power n. So the question is, so how this time scales, and whether it's n or it's 2 to the n or it's 2 to the n to the power n. And actually, this is what I want to talk about. So how difficult it is to solve these many-body problems now using quantum computers, and it will depend on the problem that we want to solve, as I will show. And on the other hand, I also am interested in seeing whether if you have now one of these NIST devices or one analog quantum computer which have some errors and maybe it's not universal, whether still you can have these kinds of gains. So this would be a practical use of these first prototypes of quantum computers. Okay, so let me start just giving some very rough introduction to quantum many-body problems from the point of view that I will need later on in order to present the algorithms for the quantum computers. So that's going to be very basic, but it will be important just to formulate what are the problems that I want to solve with a quantum computer, and also to explain why they may be difficult or easy, some of them. Okay, so that's now a typical problem that we want to solve. So this would be like a set of quantum systems on a lattice. This could be a lattice in 1D or 2D or 3 dimension. Could be different geometries. Could be like here a square lattice. Could be a hexagonal lattice. Could be any lattice. And these systems could be bosons or fermions or spins. So if they're bosons, then we'll assume that you have cut in the Hilbert space, or the dimension of the local Hilbert space is not infinite. And these particles are interacting according to some Hamiltonian. For the time being, I will consider local interactions. I will assume that the particle that is inside is only interacting with the neighbors, maybe with the next near neighbors, I mean, with some range of interaction, but it should be finite. I have to say that, I mean, it's very simple to generalize or to extend the things that I say if you have long range interactions, but at the moment I will consider local interactions to be concrete. So problems like the ones that I wrote here very in an abstract way appear in many areas of condensed matter or high energy physics. So for example, Hubbard models in superconductivity can be rephrased in the way that I did it here, or spin models also in magnetism can be rephrased in this form, or even lattice gauge theories in high energy physics can be rephrased in this form, in which now you will have maybe some two different kinds of systems. So one of them would be the fermionic matter, the other one would be the gauge fields, but they will be on a lattice in a very similar way. And so the questions that we want to address with these systems is, so first of all, properties about the dynamics. So how these systems will evolve. So imagine that I go out of equilibrium and then all these spins or all these particles start interacting with each other, then develop a very complicated states. And I would like to know, so how these states evolve in time, or in particular, how the physical property, expectation values of observables will evolve in time. And the other kind of problem is in thermal equilibrium. So assuming that the system is in equilibrium, there is no dynamics. So I would like to know what are the physical properties of the system at zero temperature, or maybe at some finite energy, or maybe at some finite temperature. So now being a little bit more concrete, so that's again the system of these particles, they're arranged in space according to some lattice with some given Hamiltonian, in which the interactions are not long range, so they're local or quasi-local. And now the problem I want to consider is about the dynamics. The first one would be about the dynamics. And it's that consider that I have a state, a simple state. So for example, a product state in which all the particles are in the state zero or in spin down, if these are spins. And then I let them interact. And then there is for a time, I look at some observable. So this observable could be some local observable like the magnetization, or maybe in a correlation function, anything that I want to see. And I would like to compute what is the expectation function as a function of time, where this psi of t is the one that has evolved according to the Hamiltonian and the Schrodinger equation. And I would like to do it with some prescribed precision. Okay, so we like to be able to compute this quantity up to some precision with some error epsilon. And what I'm interested here is how does the computational time, if I put it in a classical computer or in a quantum computer, would scale as I make the system bigger and bigger and bigger. So the scaling with n, as I was mentioning before. Of course, I will also be interested in the scaling with the error and also the scaling with the total time that I want to simulate evolution. I mean, this is something that I will not concentrate here. I mean, one can study, but otherwise it will get a bit too complicated to have too many variables. So here I will concentrate on the scaling on n, and once in a while I will mention the scaling with these other problems, with these other quantities, sorry. So in order to look at the second problem, then I have to now talk about the energy spectrum. So you have a Hamiltonian, then we can look at the eigenstates and eigenvalue, and this defines the possible energies of our system. And now we can plot the energies here in this one-dimensional diagram. So there will be first the ground state energy. This would be the lowest energy. This would be the energy that is here. And then there would be like an energy in the center of the spectrum. So this would correspond to something like infinite temperature. So that's the state will look very random there. And so as you see here, the number of states that I will have here, if you have qubits that I'm considering for the moment, it will be 2 to the power n. So I will have 2 to the n energies here. And they will have a minimum, which will be the one corresponding to the ground state, maybe a maximum will be the maximum excited state, and some energies in between. So the next question is concerns this ground state energy. So again, the problem 2, now let me formulate it. Let me consider again some observables, so some physical property of the system, like magnetization, as I mentioned before. And I would like now to be able to compute what is the expectation value in the ground state, so at zero temperature, with some prescribed precision epsilon. And so this is, I would like to concentrate on this energy and compute properties in the eigenstates, so the properties at zero temperature, physical properties. And I would like to know again how the computational time scales with n, with the number of particles. If I make the system bigger and bigger and bigger, then it will get more complicated, so the time will get longer. I want to know whether it's linear, if it's exponential, or it's super exponential. And as I mentioned before, so I may also be interested in how this scales with epsilon. Okay, so the third problem is very similar, but I have to introduce another concept that you know very well. So as you see, if I have these energy eigenstates in the spectrum, then they are more toward the center and then on the sides. So now I could count in some given interval how many energy eigenstates I have and then plot them. And as a function of the energy itself, there will be more and more and more, and then less and less and less. And this is what we call the density of states, so the number of states that are per unit energy interval. And if we take now more particles, like 15, then since there are 2 to the 15 now states, then there will be many, many, many more. And what you see is that they are concentrated in the center. And it's very easy to show that if you have local interactions, then actually this density of states will be a curve, so something like a Gaussian, doesn't have to be a Gaussian, but something like a Gaussian, and the width of the curve scales like a square root of n. And so now another important thing is that the energy is extensive. So if I have this Hamiltonian, then I will have like n terms in the Hamiltonian. So each of the particles will interact with the neighbors. So the energy would be, or the Hamiltonian would be a sum of n terms. So the total energy will be n times the energy per particle. So I would like to describe the energy density, which is the total energy divided by n, because I'm interested also to see what happens when I grow and grow and grow, and I keep this energy fixed for the next problem. So this is why, I mean, later on when I plot the density of states, instead of plotting this function as a function of the energy, I will plot it as a function of the energy per particle. So this is this En. And so for example, for n equal n, this is this curve here. So what happens now is that if I increase n in this direction, so I take n equal 15, then since I'm divided by n and the width was a square root of n, as I mentioned before, now it will be square root of n divided by n, so it will be 1 divided by square root of n. So if I look at the intensive quantities, then this density of states is getting narrower and narrower, and the scaling is like 1 divided square root of n. So in particular, in the thermodynamic limit, when n goes to infinite, it will be just like a delta in the center, and that's something that will be also very important to understand why problems get very difficult now, even if you don't talk about ground state, but also finite energies. And so with that, I'm now can present what will be the third kind of problems I'm interested in. So is fix the energy density, fix it to some number, take like before one particular observable that you would like to know, so physical property, and then compute now the expectation value of the of an energy that is exactly, well, it's written here, is n times epsilon. So this is the energy per particle. So the total energy will be E times n. So E times n. So then you go to E times n. This is this energy, and then you would like to know the properties of the physical properties at this energy. Of course, since this is a discrete spectrum, you may not be exactly at the energy where there is an eigenstate. So this is why I included here some small width delta. And so the idea is that this E can be at n times E plus minus delta, where delta is sufficiently small. And so what I would like to know is now for this finite energy, not the ground state energy, now it's a finite energy, to see how the computational effort will scale with n, and maybe also with epsilon and delta. Okay, so this would be the variables. And so the last problem is related to now to thermodynamics, to thermal equilibrium. So what happens, we know that if we have a thermal equilibrium, then the canonical state will be described in terms of the Gibbs state, which will be written like e to the minus h divided by kt, where t is the temperature, at some given temperature. And graphically, with the plot that I told you before, is that now we give a probability of a state be populated, a probability which is an exponential, that the exponential decays according to the temperature, to the inverse temperature. And so now the problem that I would like to solve is that fix the temperature, not the energy, now the temperature, take an observable and compute the physical property, namely this expectation value of this physical state with a Gibbs state, so in thermal equilibrium for some prescribed precision, epsilon. And again, I'm interested in the scaling, maybe also with epsilon and the temperature. So I presented now the problems. I hope that they're more or less clear. So let me just start talking about very briefly that, of course, you can solve this with classical algorithm. You can solve this problem with tensor networks. And it turns out that some of these problems, like for example, dynamic, or you want to solve the finite energy problem, etc., with tensor networks, the scaling with the scaling of time with n is exponential for some of the problems. I don't want to talk very much about that. You can also do exact diagonalization, then it's also exponential. There are many other problems that for some particular problems, they work very well and they don't scale exponentially. And let me just mention one of them that is very widely used. This is Monte Carlo. And in Monte Carlo, the idea is to sample configurations, yes, to take possible configurations and then to take expectation value with respect to the configurations, and the probability of each configuration is given by some law that depends on your Gibbs state. So you assume that you're in thermal equilibrium, that you have a Gibbs state, and then you have some observable and you want to compute this expectation value that I was talking before, then you just rewrite here, and for simplicity, I'm assuming that the observable is diagonal in this configuration basis, and then you see that you can write as a sum with respect to all possible configurations. So this end would be like all spins down, one up, etc., etc. And as you see, this it's a positive number. So this positive number, you can call it P of n. And then you see that it's just, you can write it as some sum with some probability distribution or some expectation value. So what you can do is to sample according to this probability distribution. For each configuration, you compute this quantity, and at the end, you average. This is, I mean, this would be Monte Carlo. And the problem is that if you want to sample according to some probability distribution, according to this probability distribution, then you will be, you have to be able to compute this number. So you have to be able, for a configuration, to know what is the probability. But this is a many-body problem in itself. So because you have to take an exponential of a huge matrix, an exponential matrix. So in general, this is difficult. For some problems, it turns out that you can approximate this probability distribution by a sum with respect to many other configurations. And for those problems, then it turns out that then you can use Monte Carlo, and then you can solve these problems. And for these problems, then it turns out that the computational time then is a function that depends on n divided by this precision squared. This is just because of the the law of large numbers, that you want to have some error epsilon, then you have to sample 1 divided by epsilon squared, and there is a function here that depends on n. And now how this function depends on n, then we don't know in general, so that's heuristic. So I mean, the worst case, it would be exponential, or it would be like worse, but in practice, so people take problems and they find that depending on the algorithm that you use, then this can be polynomial, and it works very well. So in other words, so as long as you can do this approximation, then in practice, Monte Carlo works this well. However, I mean, there are many problems that you cannot do this approximation. And when this happens, then you say that you have the sign problem, because this probability you cannot compute. And if you try to do this approximation, these Qs are not positive, so you're not able to sample according to them. And in general, this is the case. And when you have the sign problem, then Monte Carlo computational time is exponential. I wanted to say that because then with the quantum computer, we'll show how we can overcome this problem. Okay, so now let me talk about quantum algorithms. So now again, these are the problems that we had before, and I will revise the problems now and assume that I have a quantum computer, either one of these NIST devices or a quantum simulator, an analog quantum computer, and let's see how you can solve these problems. So the first thing is dynamics. So the problem in which I want to know what is the time evolution. So actually this is something that Feynman already showed, or at least said that a quantum computer would be efficient. And this was formulated by Seth Lloyd in 1996, in which what he did is he said, well, I have to take this evolution operator, and what I could do with this evolution operator is trotterize it. So I can write it as a exponential, a product of exponentials in which I divide by m, this t divided by m, and I exponentiate to m. And then if I divide by m, then I will have here an exponential of something that is very small. So the fact that the terms of the Hamiltonian don't commute with each other doesn't matter, because they will make a small error. So I can write the evolution like a sequence now of actions, yes, that act on a couple of qubits. And this is exactly what a quantum computer do, 2-qubit gates between systems. So he showed that actually then with a quantum computer, then the computational time would scale like the number of particles that you want to simulate, the time that you want to simulate squared divided by epsilon. So later on, this was improved. So now the best algorithm gives a computational time that is linear with the number of particles, that this case like log 1 over epsilon scales also with the computational time, with the time that you want to evolve. And actually, evolving and doing dynamics with analog quantum simulator is kind of trivial, because then you don't have to discretize anything. You just tune the parameters in your experiment in such a way that the Hamiltonian that is describing your system of ions or atoms or photons, is exactly the one that you want to simulate, and then you let it evolve. So for analog simulators, this is trivial. Okay, so what about ground state? Okay, so ground state, the situation is completely different. And the point is that here it was proven already many years ago that in general, computing the ground state of local Hamiltonians, it's a problem that is very difficult. So it's in the class what is called QMA, it's QMA hard. And the class QMA is a complexity class that people use in quantum computing, which is hard even for quantum computers. It's the class of problems that a quantum computer takes an exponential time when you in the number of particles that you have, but the checking that you have the right solution will only take a polynomial time with a quantum computer. So it's difficult even for a quantum computer. So then, I mean, there is no chance that we will find an algorithm that would be polynomial like the one that we found before with dynamics. So ground state is very difficult, it's exponentially difficult even for a quantum computer, even though, as I mentioned before, now you take a classical computer, then it may be faster than a classical computer because the classical computer may be like 2 to the n to the power n. Now, I have to say that there are some heuristic algorithms, so adiabatic algorithm, variational, in which you cannot prove how they work, and they may work for some problems, and this is a very active area of research. So we really have one of these niche devices. Why don't we try to solve, even we don't know if it will work, but let's try it, and if it works, then it will be great news. So I'm not going to talk about heuristic algorithms, I will talk about algorithms in which we can show that they work. And just very briefly, so how does an algorithm in a quantum computer work in order to find the ground state? Actually, the concept is very simple. Now in practice, a little bit more difficult, but the concept is that, okay, take your qubits and your Hamiltonian and prepare a random state. For example, a random product state. So it means that you take the first qubit and you put it in some direction, the spin in some direction, and the second qubit in some direction. Just take random. And of course, you now write the energy eigenstates in this form, then this random state that you wrote will be a linear superposition of the random eigenstates. And now imagine that you can measure the energy. So if you measure the energy according to the laws of quantum physics, then you will project into one of the eigenstates with a probability which will be this coefficient in front. So what you could do is to prepare the state and measure the energy. And then you will have a number. You just annotate this number. Then you take, again, repeat the experiment, you get another number. Maybe it's larger, maybe it's smaller. And you repeat it many, 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 many times. Actually, 2 to the n times or many times and 2 to the n times. So you have a list of 2 to the n numbers. And with these 2 to the n numbers, then just choose the one that is the smallest, and then very likely, then will be the energy of the ground state. And so you repeat the experiment until you get this energy again. And when you have, you know that your state is exactly the ground state. So you have prepared the ground state. So this, of course, I mean, you can do it more clever, not annotate the numbers, but only if it's smaller than the previous one and so on. So you can do it more efficiently. But typically the probability, since it's a random state, will be 1 divided by the 2 to the n, by the total number of states that you have. So you will have to repeat an exponential time, and this will give you an algorithm that would work in a time that goes like 2 to the n. But we know that it cannot be, I mean, much better than that. It has to be exponential. The only problem with this method is that it's very difficult to measure the energy, because the energy is like a many body observable. So typically you can measure 2 body observables or single body observables. And if you indeed measure each of the observables by themselves, then you get expectation values. You don't project your eigenstate, so this will not work. And so this is why you have to use some other methods that were developed in the context of quantum computation. So one is what is called phase estimation. And phase estimation, basically, what it gives you is that if you have some linear superposition like the one that we had before, then you will put some extra spins, some extra qubits, and then you do a unitary operation in which it copies the energy of the state here after the I mean, in this extra qubits. So now you can measure these extra qubits, and this is like measuring the energy. It's a little trick. You can also use what is called amplitude amplification or Grover's algorithm to do it more efficient. And you do that, and it turns out that this method works. I mean, the computational time goes like 2 to the 3n divided by 2. Actually, some time ago, we figured out a method that is more efficient than that. It uses something more sophisticated that is called a spectral filter. I will not talk about that, but that's, as far as I know, the most efficient algorithm runs in a computational time that works like 2 to the n half. So still exponential, but it's 2 to the n halves. Okay, so now I want to go to the most important part of my talk, which is now quantum algorithms for finite energies and finite temperatures. So the problem, let's say 3 and 4 that I mentioned at the beginning. And the first thing that you notice is that the problem 3 you fix the energy density, and then you would like to be able to compute expectation values at these energy densities, well, I mean, basically, it's a generalization of the ground state, because the ground state is a possible energy, so it cannot be simpler than the ground state in general. And this means that in general, it will be very difficult because it contains the ground state problem, which is exponential. And in fact, so people have developed some algorithms, but all of them are exponential for this problem that I'm considering here. So one strategy is to try to prepare this Gibbs state, for example, or this energy eigenstate, and using some imaginary time evolution, but with a quantum computer, it can run very well real-time evolution, so according to Schrödinger equation, but you cannot do the imaginary time, so you use the tricks, and by using these tricks, then you get this exponential scaling in the time with the number of qubits. Or you can also find a quantum version of Monte Carlo. This was done in this version, in which now the quantum computer is not sampling configurations, but is sampling superpositions of configurations, but this method is also exponential in general. So I want to here to present two algorithms so that solve these problems that I mentioned, problem number 3 and problem number 4. And so the first one, actually, it turns out that we can prove that it's efficient. So it can find for a given energy and a given delta, they can find these properties in a time that only scales polynomially with the number of particles, at least for some energies that are not the ground state. But these are some energies which are finite, so it doesn't have to be infinite energy. So it will be finite. And so this is what I want to show. And it turns out that for that, if you want to use this algorithm in practice, what you will have to do is to implement the dynamics for a time that will be of the order of the number of particles. And you will have to do many, many, many measurements. So the idea is that you can really solve this problem efficiently. You can prove that this is an algorithm that is efficient. The price that you will have to pay is that you will have to run this algorithm for some time, but we know that this can be done efficiently because it's for simulating the dynamics, and you will have to do many measurements. The second method will be sampling. So it's a method that builds on top of this other algorithm and does sampling. And you can, with that, compute micro-canonical and canonical variables. So you can solve problem number 2 and number 3. And the idea is that you use the Monte Carlo, as I told you before, but you remember that it's very difficult to compute something, this probability to sample if there is signed problem. So this overcomes this problem. So actually what this algorithm does is compute this quantity with a quantum computer, and then once you can compute this quantity, you can sample classically, and so you use the rest is classical, and the price that you will have to pay. So actually this runs for times, the times don't have to be of the order of n, so the times that you have to run the simulator are of the order of 1, but you will have to do many, many more measurements because you will have to sample. And as I will mention, you will see, since they have, what you have to do is to run evolution, to solve these problems, you will have to solve dynamics as a subroutine of the problem that you want to solve. Then they can be applied to NISQ and quantum simulators. And in fact, we studied them numerically and show that they tolerate some errors. Okay, so again, let me go to the problem number 3. You have this density of states that I mentioned before. This is the energy per particle. This is the number of particles that you have. You fix the energy density here, and then you increase the number of particles. And you see already here what is the problem, is that if I'm increasing more and more and more particles, the fraction of states that are with that energy goes down, because all the states are here in the center. So they're more difficult to find. And that's, what is behind that. Of course, the ground state, which is here, is an extreme case. And it's very difficult, but if you're here, then in principle, one could think that this could be difficult in practice. But as I will show you, this is not the case, and the idea would be the following. So the algorithm that we propose, that's the following. This is the density of states again, and now this is now the extensive energy, so the total energy. So you fix for a fixed value of n, you fix this energy. And so what you will do is that you will prepare a state with your quantum computer that will be easy to prepare, and that this has this energy as expectation value. Of course, it will not be an eigenstate, it will have some spread, and actually this spread will be very big. And so this state will be useless in order to compute physical properties because it's too broad. However, in the second step, what you will do is to make it narrower. So you will apply some filter in the same way that we apply filters in optics when you have a spectrum that is very big and then you filter something. So here we will filter in a way that will make it narrow, 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 very narrow, and as narrow as you want. And then at the end, so you will have a state. And in principle, you could prepare the state, but as I will mention, this state is very difficult as a linear superposition of many states. So it looks like a big Schrodinger cat, and it may be very difficult to prepare it in practice. So the idea is never to prepare it, but instead to do some, to apply some evolutions, to compute some quantities without preparing the state. So you will understand it, what I mean, that you never create the state, but you compute the things that you would have obtained if you had that state. You will understand it in a second. So let me go a little bit through all these points. So the first one is that you give me some energy. And the first thing that I do is that I prepare, for example, an easy to prepare a product state of my qubits. And I prepare the state. And this state is not an eigenstate, but I prepare a state, I choose the qubits in the state in such a way that the energy corresponds to the one that you're asking me for. And so the state will be a linear superposition eigenstate. It's not an eigenstate. So this is what I said before, that you will have some, let's say, width in terms of the energy of the states that form them. And this, you can show that actually it scales like a square root of n. So you take a product state, the width is a square root of n. And that's not good enough, actually, because if I would now take and measure observables with this state, then since they are product state, they will find no correlation at all, because product states don't give correlation. So this state cannot describe, let's say, the properties of these eigenstates, because this eigenstate will have correlations, but this state doesn't have correlation. And the reason is because it's too broad. So that's why, well, actually, I mean, you could say, well, how can I make sure that I have a product state with this energy? Actually, you can prove that this is always possible as long as this energy density is larger than some value, some finite value. So there's always some interval, some intensive interval for which this exists. And if there is no product state which fulfills that, so you're asking for a low energy. So as long as you can use any algorithm to prepare this state, then this algorithm will work. Okay, so now the second step is to make it narrower. Well, I mean, this is a restriction, of course, okay? So you have to be able to prepare a product state or an easy preparable state with this energy. And this precludes you from using this algorithm to find the ground state, because you ask me to take the ground state, then probably I will not be able to prepare it. Okay, so now how we reduce the variance? So the idea is to apply a filter, as I mentioned before, just to take the product state and to apply some operator, which depends on your Hamiltonian. That's a filter operator that will make it narrow. And this operator could be, for example, a Gaussian filter. Is some function, some operator that is centered at the energy that you want, and it's a Gaussian of a width delta. So this will make it just narrower. And this Gaussian operator, the problem that it has is that you cannot apply arbitrary operators to states. We know how to, the only natural operators that we can apply to states are measurements, but we don't want to do measurements at this point because we will have a random outcome, or rather to apply unitary operators, okay, and evolve according to Schrodinger equation. So that's why what you can do is to write any of these states. You can do the Fourier transform and write it as a sum of states which now are evolution operator. So this means that what you will do is applying this state is actually generate a linear superposition of evolved states for different times, and in which these coefficients for each of these evolution time you can compute classical, it's just a combinatorial number. Okay. So some remarks. So again, so this is the original state. Then you will apply this operator, and I'll show you how to do that. And then you have this linear superposition. And the first thing that you notice is that the number of terms that you have in this sum scales like the square root of the number of particles, and delta, it will scale on how narrow you want to make this. So if delta, I mean, it's a square root of n, then you don't have to do anything, because this was a square root of n, but if you want to make it smaller, then you will have to add more and more terms. And also the maximum time that you will have to evolve your system in this superposition scales like 1 divided by delta. And it's very easy to understand that by Fourier analysis. The other thing that is remarkable is that this state is not normalized. It's not normalized. So this means that if we want to prepare this state, we will have to do some measurements. Then it will be probabilistic, and probably you may lose this efficiency. You will get some output with some exponentially small probability, and therefore you will lose this probability, this property. And the second thing is that this can be very entangled because it's a superposition of many product states. So if you have any decoherence in your system, then it will be not good. Okay. But the third point exactly takes care of that, because you say, well, at the end, I don't want to prepare the state. I want to compute some expectation value with that state. So you can write the expectation value of that state with this. And if you just write it down, then you realize that you can write it. I mean, don't enter the mathematics, but you can write it as long as you can compute this expectation value. So you have to be able to compute an expectation value of the evolution operator with your product state and things that are very similar. So the idea of the algorithm is to measure this quantity. So to measure, never prepare the state, just find a different way of measuring this quantity. And once you have these quantities, replace them in this formula and do a classical computation. And of course, the number of quantities that you have to measure will increase, like the number of terms that you have in the sum, plus the number of measurements that you have to do. But this will be polynomial, because I mentioned before that things are polynomial. And then once you have measured with a quantum computer these expectation values, then, or these quantities, then you, in a classical computer, you just do this computation. And so, I mean, don't want to enter into detail, but actually there is an algorithm that you can use that's simple. So basically it's related to measuring Loschmidt echo. So you start with some product state, that's the product state that you prepare in your system with your qubits or your spins, then evolve for a time. And then you look at what is the probability that you're in the original state. And if you measure this quantity, you can retrieve this A of t, or the absolute value of A of t. The phase can be retrieved classical. Now there are many details, but that's the way how you can compute these quantities. So altogether, so again, if you look at the problem number 3, I give you some energy per particle, some energy density. Then you want to see how you can compute with certain uncertainty here, delta. What are the physical properties? I gave you an algorithm here that what does is creates a product state, then evolves it for some times and measures, then do it many times for many time steps and repeating many times to get the expectation values. And at the end, you compute the expectation value in the classical computer. And you can see that the time, the computational time actually is, grows polynomially with n. Actually, it goes like n to some power n to 3/2. It scales like it scales like 1 divided by delta, and it scales like epsilon. So actually this already, there is no classical algorithm that is known that has this scaling. So all classical algorithms will have some exponential here, either exponential in n or exponential in delta instead, or in 1 over delta. So this is already an exponentially more efficient than a classical algorithm. In fact,
question. So don't you get some small denominator problem in this evaluation of this Loschmidt echo? Because typically they become exponentially small at some finite time delta, right? So doesn't that mean you need exponential number of measurements somehow, or?
Actually not, actually not. Okay. Actually, when we can prove is that it doesn't go. So for the times in order to get this value of delta, then the denominator is not exponentially small. It scales also like 1 over delta. Of course, goes to 0.
Exactly, right? Yeah, that's what I'm...
But for the times that you require in order to get this number, it's not exponential. I mean, this is proven this can be proven mathematically. So
okay, yeah, I was wondering.
I don't have an intuition for that, but there is an statement. It's a very good question, and that's the hard part to prove that mathematically.
Exactly, yeah, because I would normally suspect that estimating the required numbers would be exponentially hard, but
it turns out not. So you formulate the problem, then I can tell you that it's not. So it scales. Okay. I mean, if you want to get the precision epsilon, you want to get that, then it scales like polynomial. So the whole algorithm is like that and takes into account the fact that the denominator is going down. Yeah,
nice.
Can I ask a different question quickly? Is there any complication if the ground state is degenerate on these?
Well, what happens if you apply an algorithm to compute the ground state? So probably all the algorithms that I mentioned and that I know will not select one of the eigenstates. The problem is more than the degeneracy is the gap. So if the gap gets smaller and smaller, then typically the algorithms take longer time. So in fact, the method that I gave you before that scales like 2 to the n 3/2 assumes that there is a gap that is independent of n. Otherwise, you will get a function of the gap in front. And there is an algorithm that doesn't care about the gap, and it scales like 2 to the 2n. That's a good question as well. And but so there was an assumption there in the classical algorithm, and in the quantum algorithm. In the quantum algorithm. And what will happen is that typically these algorithms will not select the ground state. You will get one of them and it will be a linear in one state in the subspace. But the problem is more the gap than the degeneracy.
Yeah. Okay, thank you.
Good. Okay, So now, so one can wonder, if I want to retrieve thermodynamic properties, so I want to get, make the system bigger and bigger and bigger, but I would like to know what is a thermodynamic property, so an intensive quantity. So how does delta have to scale in n to get a sensible value? And it turns out that this has been studied, and if you believe ETH, this eigenstate thermalization hypothesis, that's a technical point, then this delta scales like 1/n. So still you have a polynomial algorithm to find to solve this problem. Okay, so I moved now to the last part, which is this quantum algorithm that it's related to sampling. And now the idea would be, I mentioned that before, is to use this quantum computer in order to compute the quantities that you need to sample configurations. Okay, so you will sample configuration like quantum Monte Carlo would do it, like the method that I told you before. But if you have the sign problem, quantum Monte Carlo will not work. But now, because you will have to compute quantities that you cannot compute, and now this quantum computer would be used in order to compute this quantity in such a way that you don't have sign problem and that the method works. So the idea is a quantum computer will be like a subroutine of your classical computer. And the idea, first of all, is that if you, like before, choose some energy, fix some energy and some interval delta around, then an expectation value of the observable, now for this particular energy, then can be written in this form, is the observable at some energy, and then you weight it with some Gaussian function that has a center around some energy E that you're interested in with some width delta. And if delta is sufficiently small, then this will converge to the value that you want to measure. And it turns out that it's very simple algebra, that you can just rephrase this in terms of this operator that I defined before, this Gaussian operator. So you can really rephrase this quantity in terms of this, these quantities A and B that I mentioned before. So it means that with the same protocol that I told you before, you have to modify a little bit because the formulas will be a little bit different. So measuring the same quantities as before, then you will be able to compute efficiently this P. And if you're able to compute efficiently this P, then you will be able to sample efficiently. And everything is polynomial and so on. So everything works. So this is why, in order to compute, now this would be micro-canonical ensemble, you fix the energy, you fix some interval delta before, then you could do it by sampling with Monte Carlo, in which now you use the quantum computer to compute the probability of each of the classical configurations that you want to sample. There is no sign problem. It turns out, I don't have time to detail it here, but it turns out that you need delta of the order of 1 in order to recover the thermodynamic variables. However, this requires more measurements because you have to sample, apart from computing this A and B, then you have to do it for each product state that you sample, and you have to do it many times. So but still the number of measurements scales polynomially with 1/delta and n. And so this is just some numerical illustration. So we took a model that we can solve with a classical computer efficiently, and we can solve with this classical computer. There's a typical model, an Ising chain with a transverse field. So we can go to larger systems, and then we can just simulate how the quantum computer would behave here, and if it would have errors and so on. And so that's how we solve for this model. This model, probably you know that depending on G or H, there is a quantum phase transition at G equal to H. So if H is large, then it's a kind of all the spins will be in the C direction. And if G is large, then then there will be this order. So it will be, the spins will be pointing in parallel, but will not decide whether in the X direction or the minus X direction. And so what we did, is to plot now exactly, and also simulate this model, this method, this sampling model that I mentioned before. This is for 20 particles, for 100 particles. Let's say in the case where you are above the critical point, the case that you are below the critical point. And then we plot for two different values of delta equal 4 and delta equal 1. So the points is Monte Carlo, the straight lines is the exact result. And you notice several things. So the first thing is that you get a different result here, but if you increase n, then even delta is large. It doesn't go like 1/n. They are getting closer and closer and closer. And that's what I mentioned, that if delta is equal to 1, then you will converge to the thermodynamic limit. The second thing is that there is not a very big difference between being above or below the critical point. The only thing is that at some point, when the energy is too low, is even lower than the ground state energy, then you don't get very precise results. And in fact, the exact method that we use in order to compute that, because you have to fix the energy and so on, then was not allowing us to compute things for 100 particles below certain energy. And this is why we have the simulation with the Monte Carlo method, but we cannot compare with the other one. What we did also is that we included error, 1% of the error in all the measurements, and to see what happens. And you see, well, maybe you cannot see it very well, but I mean, there is not a big departure. So the results are of the order of 10 to the minus 2. So they're small compared to this plot. So this means that you had errors like the ones that Google has in the quantum computer, and maybe a little bit better because they have big errors in the measurement, but you have errors in the measurement that would be of the order of 10 to the minus 2, then you could still compute these things with these NIST devices. And yes, you can adapt now for finite temperature. So you have the Gibbs ensemble, and you can also rephrase it in the same way. I don't have time to do that. So we did the same thing, and then we plot it not as a function of the energy, but as a function of beta, 1 divided by the temperature. And we also see that the exact result, these are the straight lines and the points, which are the ones using Monte Carlo with delta equal 1. I mean, they give good results. And if we put 1% errors in the measurements, then you see also that, I mean, they kind of give a very reasonable result. So with that, I want to conclude. So I have talked about quantum many-body systems and how you can solve, well, these problems are very difficult in general. So fortunately, there are many classical methods that work in many interesting situations. In some situations, these methods don't work. And there is where a quantum computer could be useful. I gave you algorithms, and I told you that the dynamics is very clear, that it will be able to do it very efficiently. But for thermal equilibrium, that's more difficult. And for zero energy, then it will be an exponential problem in general, even though there are some heuristical algorithms that may be better. But for finite energy and for finite temperature, I gave you some algorithms. And I showed that for final energy, if it fulfills certain condition that is not too low, is not close to the zero temperature, then you have a polynomial time algorithm, and there is an exponential speed up as compared to the best known classical algorithm. For the other method, for the one that samples, actually circumvents the sign problem for Monte Carlo, and they seem to be relatively robust because we did some simulations with errors, and they seem to be good. Now, this means that probably they are useful for NIST devices, and so we are talking to people who have these NIST devices and analog simulators in our group, and also Michel Looking and some other people in Harvard and in our institute, and so they're planning to implement them. And the requirements is that you have to be able to prepare the state with that energy, like product states, and then you have to measure this Loschmidt echo, so the probability that you return to the original configuration. And what we are looking at the moment, so we are looking now at more specific errors that they have in the experiments and to see whether they will work. So for example, if they have problems by detecting single spins very well, then maybe you can do some coarse graining. So we're trying to see whether we could do some kind of coarse graining. And also we're looking at some other quantum algorithms based on the same idea, which is don't prepare the state, filter and measure and use as a subroutine. And also we are looking at classical algorithms that are inspired by this method to see if we can speed them up. So thank you for your attention.
Okay, thank you, Ignacio, for a very interesting talk. Are there other questions?
This is Kyle, and this might not make sense, but when you rewrote, like sort of step 3, you said don't actually use the state, but you rewrote it into the appropriate form, and then there are these basically coefficients that you need to measure. I'm just wondering if, in a different context, which is not about using quantum computers to do these kinds of calculations, but in work where people are, for instance, trying to extract measure these quantities from, for instance, lattice simulations and things like that, if a similar kind of trick can be used where instead of calculating these expectations directly from a bunch of samples, the problem is recast into trying to estimate those coefficients.
Yeah, that's right. That's in the context of tensor networks, that's what I meant by this inspired classical algorithm. So in fact, what you can do is to take tensor networks and to use tensor networks in order to compute these quantities, A of t and B of t. And as I mentioned before, these quantities for this, I think it was here, you see, in order to compute these quantities, you need this delta of the order of 1. So it means that you have to compute the evolution of a quantum many-body systems for times of order 1. So let's say if you have some J energy scale that is J, so it will be 1 over J, no? But it's a typical, that does not increase with the size of your system. So you have any classical method that is able to compute the evolution for a fixed amount of time, then you can automatically use this trick and to use in order to overcome the design problem in Monte Carlo. And that's exactly what we are doing in our case with tensor networks, because we know in tensor networks how to do time evolutions for short times. For longer times, entanglement explodes, so they don't work, but for short times they work. And that's what we are doing now, to combine this method, not with a quantum computer, with a classical computer. So thank you for the question. I think it's very good. And it would be interesting to see other methods that people use that can compute these quantities, because then they could be combined with Monte Carlo to circumvent the sign problem.
So Ignacio, I still have a question related to my earlier one. Also, it's that, so in this method, you need to extract the Loschmidt echo exactly, right? So you don't need to extract the return probability, which means that it depends on the phase, right? So it seems to me like if you have an ordinary quantum simulator, you wouldn't have easy access to this phase, right? You would just get the square of it.
That's a very good question. That's a bit more technical. So actually I have a transparency here where I said that in fact, the Loschmidt echo will give you this quantity. I don't know if you're seeing it in your screen.
Yeah, I see it, yeah.
Absolute value, but actually you require the whole A, and the phase is important.
Exactly.
But it turns out that if you take many models, like Hubbard models and spin models and so on, this phase you can calculate classically. Okay. And the reason is because there is a non-trivial symmetry. There is a particle hole. It's not a symmetry. It's something similar to a symmetry. And then because of that quantity, then you can compute this exactly, except for the sign. So it turns out that you can compute not the sign. But then what you can do is that you can compute the absolute value and see when it gets 0.
Yeah, and then you just
whenever it's 0, then you know that thing's a sign. I mean, it could happen that it only touches, but then you can
but then it should be analytic when it. I see
exactly.
how you fix it.
Even derivative or other, so you can retrieve it efficiently.
But it would restrict kind of the class of models you can do it on if you can't do phase estimation. So the other way is to kind of do phase estimation.
Exactly. Well, you can do phase estimation, then you can compute it with a quantum computer. You have an analog quantum simulator. There is this trick for certain kind of models. And actually in the paper, we have some other trick for more general models. And the idea is to use some ancillas. And so you have to be able to prepare an eigenstate of the Hamiltonian, and you can prepare an eigenstate, you can do everything. Of course, it's, when arbitrary Hamiltonian, you cannot prepare eigenstate. What you can do is that you can put, let's say, some ancillas, and then in a trivial Hamiltonian, so that the eigenstate is trivial, and with that is enough in order to do that. So there are some tricks, but it gets very tricky.
So is that what you're trying with Misha, like to do kind of phase estimation with Rydberg blockade to extract it, or?
Actually, so Misha can measure the Loschmidt echo very
exactly. Yeah.
And so we have had some discussions. Still, they have not materialized to anything. But the idea is to take one model in which this trick would work.
Oh, yeah. Nice, very nice.
So I see that there's a question from Juan. Maybe you can just ask it. I saw it. It's rather long in the chat box.
Yeah. So I mean, I'm far from knowing all this, but I was reading some papers, and I am more into the high energy theory. And there are some concept of complexity that now are being studied. And for example, the thing is, if we have a space, a Hilbert space, and we have a state, and we have another one, and basically we can, if you want to discretize, and we can use gates to go from this state to this one, we can say the complexity that gives us basically the minimum amount of operations or basic operations to go from here to here. Is there a way, for example, to use those ideas to reduce the time of computing if we know, for example, which is the complexity? And for example, also I was reading that we can think of the space of operations, and we can calculate like geodesics and tell us, okay, from going to here, this is the best curve we can have. Can we use those ideas maybe in here?
Well, I would say here I have been concentrated in Hamiltonians, and therefore the dynamics is somehow dictated by the Hamiltonian. Now, what you say, I mean, may happen that there is a more efficient way than using the Hamiltonian itself in order to compute the properties of the Hamiltonian by using some shortcut, but probably it has to have some relation to the Hamiltonian, because you want to compute properties of your Hamiltonian. So in that case, I don't see any trivial way or any direct way of doing that. Another thing is that if you change the problem, if your problem is not now that you want to create, let's say, some properties of a Hamiltonian, but you want to look at properties of some states, namely, you say, well, there is the Laughing state, is a wonderful state, or some, I don't know, so ETA state that appears in high energy physics, some states, and this extracting properties from the state is difficult with classical computers, but if I could prepare it with my quantum computers and could extract properties, then yes, then of course, any shortcut that would allow you to prepare that state, as you mentioned, then would be good. And in terms, I mean, I'm aware of the people looking at these complexity questions in order to define, let's say, equivalent relation between states, then it will be very important, not only to find equivalent relation, but to find optimal ways of finding connections to prepare. This would be for a different problem though.
Thanks.